What's up, guys? Today, gonna be talking about another cool CodeForces problem that I found. Chip game. So let's get into it. So we have two players playing an old Birria game. Not really sure what that means, but yeah. So there's a chip at the lower left corner of the board, and you can move that chip up, right to the right, or up by any odd number of cells. So it could be like 1, 3, 5, 7, 9, or so on, and the person that can't make a move eventually loses. So whoever can't make a move last loses the game. So if we want to win, we got to be the last guy to make that move. Burenka goes first. I don't really come up with these weird names. Yeah, so Burenka goes first, and then Tonya goes second. And apparently Burenka's too lazy to come up with strategy, so we got to find out who wins based on the board. So, and they both play optimally. So, seems like the question is trying to ask us based on the dimensions of this board, who will be the one to win for sure, guaranteed. So, with that, that's with Birenka going first, of course. So yeah, and our constraints are we get about 10 to the 4 test cases, and we have for each test case we have two integers n and m, which can be ranging from 1 to 10 to the 9. And for the reason why I kind of like take these constraints seriously is like they can help you sort of like see what kind of solution you need to come up with. So in this case, if we have 10 to the 4 test cases and 10 to the 9 dimensions, generally I'm seeing more of like an O of 1 solution because we can't iterate through the whole grid, since that would be, well, n is 10 to, in the worst case, n is 10 to the 9, m is 10 to the 9, that would be 10 to the 18, and multiply that by all the test cases, 10 to the 22. Yeah, the computer usually runs, and there's a 1 second time limit, so it usually runs like 10 to the 7 operations per second, 10 to 8 maybe if you want to push it. So we definitely need like an O of 1 solution, so, or like in other words, a constant time solution, as opposed to iterating through the whole grid and finding out. So let's see what we got, right? So I'm gonna draw a grid, right? So I already have a pre-drawn grid here, 5 by 6 actually. So n is 5, m is 6, and the way I went about this is like, okay, so we know we start at the lower left corner of the board, and we can move either right or up, and we want to end up in that top right square essentially. So I started like with the most basic scenario. So if we have like, for example, a grid of just one square, well, we know that in this case, Bianca has to make that first move. She has to move either right or up by an odd number. So she has to move like 1, 3, 5, or so on squares. And if there's only one square, well, she can't really move up or down or upward to the right because there's nothing there. There's only one square. So in this case, if I'm first, if I'm at this square and it's my turn, then I'm gonna lose. So therefore, in this case, we would print out Tonya, the second person, player two. She's the one that's gonna win because the first person can't even make a move at all. So it's just about which person can't make a move at the end, right? So if we're going to a more complex board, or actually let's go with like a grid of two now, like two, 1 by 2, right? So 1 row, 2 columns. So if I'm Birinka, I can if let's start from like the back square. So if we're at this square, we know that if you're at this square and it's your turn, you're gonna lose, right? Because you can't move anywhere. But if you're at this square, you can move one to the right, which ends up at a losing square. So in this case, we're gonna win if we're at the square, because then we could just move one to the right, and whoever's turn next, that's the person that's gonna lose. That's our optimal strategy, right? So if Bianca's going first, then she's gonna be the one that wins because she's here and it's a win state square. So in that case, she's gonna win the game, and therefore we would output, instead of Tonya, we would output Bianca. I'm not gonna spell the whole name. I'm just gonna do the first letter. So now moving on to like a more complex square, we can do that same strategy of like moving from the top right. So in these cases, there's only 1 row, but if we have multiple rows, let's start from the top right because we know that in here we would lose since we can't move to any other square right or to the up, or going to the right or going up, right? But if we're at this square, we can move 1 unit to the right and give us a win condition, right? And if we're here, we can move 1 up, and that would give us a win condition. Because we just move 1 square up, and that would give us that that give the other person who's next that lost condition. And yeah, we keep going, right? So if we're at this square, we can then, okay, we don't want to give we don't want to give that person a win condition, um, but we can't actually. So we would want to optimally go to this square to give the next player's turn the lose condition. But the problem is we can only move an odd number of squares um, to the right or up. So therefore, we can't actually move 1, 2 units up. That's 2 units over here. That's not odd, right? So we can't actually do that. And if we move 1 unit up, and we can only move up, by the way, we can't move to the right because obviously that's going outside of the bounds, right? So we can't move up because, well, that would lead us to give the next person a win condition, and we would lose anyway, right? So we can leave only two options, and they both lead us to bad situations. So therefore, this can be a loss to here. And we keep building up this tree. So here it's the same idea, except moving to the right. We can't move uh, 1 unit to the right because that would give the next player a win condition, and we can't move to L because it's like 2 units. So that will also be a loss. And you can kind of see like a pattern here. So like, let's start with this guy now. So at this state, we can either move to 1 unit to the right or 1 unit up. But the problem here is, well, that would lead us to give the next player a win condition each time. So that'll be a loss. And we keep building this tree. So here we could do the same thing. So we can either move 1 up or 1 to the right, and that would give the other person only lose conditions. So that would be a W, right? And here, same idea. If there's ever a chance we can give the other person an L, then we would win the game, right? So now this here would be W, W, and you can see the pattern, it's like alternating, right? So here, W, L, L, and we could continue finishing this whole thing. And if I finish this up, we can see that, okay, well, boom, boom. I'm just going to finish writing this whole entire thing. And kind of like see how we're kind of like working backwards from like a base case and then building off of it, right? So, and this is how we would populate this grid if we didn't have like an O of 1 restriction on our time complexity. So this is what we have, and we can see here if we start at this square, that means we're gonna win the game. So in this case, Birenka's gonna win the game, right? And this is when n is equal to 5, and when m is going to be equal to 6. Okay, so that's what we have so far. But when would this actually be something that isn't a W? Like, when do we know when Birenka's going to win, when she's not? And then for this grid, she won, but how are we going to make that based solely on the values of n and m, which is the only input we're going to get from the test case, right? So in that case, then, okay, well, we know that if we're alternating, so it's gonna be like L W L W L W, right? So if it's you can kind of see, okay, well, if our starting condition if our like starting condition is like our starting square, the dimensions of the starting square, if it's sort of like of different, it has something to do with the parities, like whether it's odd or even. So here it would be, I think we're going 6 back, so 1, 2, if it's 6 columns, then our first column is going to be of different parity than the n column, right? W is different than L. So when I say parity, a parity means like odd or even. And if, so for our rows, if it's of the same idea, if it's odd, then we're gonna have the same parity. So you can see that if we have like if it's even parity in the number of columns, then these two characters are gonna be different. And if it's like if it's something like odd, where 1, 2, 3, 4, 5, something like this, if it's like odd, then it would be the same win condition. See, because we alternate, right? So we can kind of like generalize this, and we can say that, okay, well, if this, so that would mean our starting condition, our starting square, which is we can call it 1, 1, because I believe this is going to be like kind of like one index type thing. So if we call this 1, 1 as our beginning, and the ending square is it's going to be, we call it, let's say, n, and then m, where n is the number of rows and m is the number of columns. And let me just erase this real quick. That's a highlighter, that's my bad. Whoopsies. Yeah, there we go. So if this, okay, so if here, if we have, so we know it's always going to be an L in the n m squared. So if it's of different, if m plus m is like, for example, odd, or actually we should just say like, let's break it down a bit. So if we have, let's say, an odd number of columns, or actually in this case it's even, so an even number of columns, that means this column here is going to be a W over here, and then we have an odd number of rows, it's going to be the same parity. So basically what I'm trying to say is even means different, and I'm sorry for the, actually let me just use text right here. I'm new to this, so let me just pull this out. So I'm gonna actually write this out. So even means different, because 6 meant like the first is different from the last, and odd means same. Okay, so in that case, I'm gonna move this down. I'm actually expand this a bit. Means different, odd means same. So if we have an L, so like if columns is, the number of columns is odd, that means first column is going to be L as well, because the top right's always going to be an L. And if it's even, first column is going to be W. I'm gonna expand this out a bit too. Whoops. Can't. I'm so bad with technology. There we go. All right. And then for rows, if it's odd, then our first row, and for odds, it's gonna be the same idea, right? If it's odd, then the first row is going to be, so in this case it was odd, so the first row is going to be L, and if it's even, the first row is going to be W in a sense. So we don't see that here, but if this was like 6 or like 4, it would be different. So if we have, for example, an odd number of columns, so odd number of columns, and that means, and then even, we're going to consider all the cases. So we can either have, for the pairings, we can either have odd columns and even rows, even columns and odd rows. We could have odd columns and odd rows, and I have to expand this out every 2 seconds. I hope it's not too hard to read. And then even columns and even rows, right? So if that's the case, so we can go, there's only 4 cases, right? Because it could either be odd or even for each both columns and rows, and 2 times 2 is 4. So let's handle each case individually. There's only 4 cases, right? We have odd columns. That means our first column is going to be an L, and then since it's even for the rows, that means we're going to switch it. We're going to switch what the win condition is. So we're going to go from L to L to W. So in this case, we're going to win, right? If we have, now for even columns and odd rows, that means we'll have, we're going to have a W, we're going to have L to W, because even flips it. And then for odd rows, we're going to then, for odd, we're going to keep it the same. So that will also be a W as well. So that means we're going to win in this case too. But if it's odd columns, we're going to keep it the same. And then we're going to keep it the same for the rows because it's odd. And that's going to be a loss. And then if it's for even, it's going to be, if it's even, we're going to change it up to W. and then if for rows, we're gonna then change it back to L. So therefore, we're gonna have a loss here, and you can kind of see a pattern now. If we so not a pattern, but we have all the cases, and we could write it like, now that we have the answer, we can sort of write, okay, like if m%2 is equal to 1 and that's just checking the remainder, right? It's equal to 0, then we could say, okay, we win, and we could do that for each case. But we can go one step further, and we could be like, okay, yeah, then that means Barenka's gonna win, and these are all for Barenka because she's the one that's gonna go first, right? Then we'll be like, okay, yeah, Barenka wins the game, right? But we can do better, because what is the sum of an odd number and an even number? So what is odd plus even? Because these are both odd plus even, right, for both these cases. And if I try a sample one, 3 plus 4, that'll be 7. So therefore, it's odd, right? Same idea for here. You're going to have even plus odd. So like 4 plus 3 is equal to 7. So we know this can also be odd. And then if I go here, we have like odd plus odd, which is equal to, okay, 1 plus 3 is equal to 4. So it's even, right? And then we'll have like even plus even, which is going to be even, right? Because 2 plus 2 is equal to 4. That's also even, right? So in that case, we can just essentially, for these two cases where we actually win, the sum is going to be odd, because in both cases it's odd, and in these two cases the sum is even where we lose. So we can then generalize this really easily into a one-liner, right? So if n plus m, the number of rows plus the number of columns, %2 is equal to 0, well then we're gonna lose, right? So that means we're gonna print out Tonya, the second player, because she's gonna be the one that wins. But if it's odd, then we can basically print out Barenka, because she's the one that's gonna win. She's the one that goes first, and that's it. That's our answer. We're just gonna add up m plus m, and then check the parity, and then see whether it's even or odd, and we could tell instantly whether it's Barenka or Tonya, and we could test that out, right? So we said that if it's even, Tonya's gonna win, and if the sum is even, Tonya's gonna win, and if the sum is odd, then Barenka's gonna win. We can check out in test cases. 1 plus 1 is 2, that's even, Tonya wins. 1 plus 4, that's odd, Barenka wins. 5 plus 6 is odd, Barenka wins. 2 plus 2 is even, Tonya wins. 6 plus 3 is 9, Barenka wins. And for this one, this is also odd, Barenka wins. And you can see, like, well, there we go, right? That's probably our answer. Let's test that out. So I'm gonna implement this real quick in C++. You can do any language you want. I just like C++ because it's like easiest for me, at least. So I get T, read in T. Then I'm gonna read in N and M. Then I'm gonna check. Okay, so if m plus m %2 is equal to 0, then if it's even, we said Tonya's gonna win, but I'm gonna do it the other way. I'm gonna do if Barenka wins, Barenka, and then else Tonya is gonna win, and that's basically it, right? So let's run this, see how it works. So, 4, it's not printing. Oh, there, it's just a bit slow. Tonya, Barenka. We could test that out, but oh, I spelled Barenka wrong. It's supposed to be Burenka. Weird names. Let's print this out. See if that works and see if we get accepted. It's a bit laggy. College Wi-Fi. See, and yeah, it looks like it works. So yeah, that's how you do it. So you can see like how we kind of like broke it down into like steps. So for a chip game, we were just like, okay, well, it seems complicated at first because you think of a grid, but you don't realize that we can maybe just use the dimensions, and like you see how the constraints are hinting at like an O of 1 solution. And since they're, you know, N and M, since we have N and M and we can come up with an O of 1 solution, we came up with like, you know, the idea of breaking it down to first the base case, having like one sort of square at first, and then having 2 by 1, and then seeing how we can start with the top right. We know instantly who's going to win, who's losing, and we could break it down by building off of that, and eventually coming up with a one-liner by breaking it down just into numbers as opposed to like visualizations and creating like 2D arrays that we don't need, right? So yeah, that's the beauty of a CP. It's kind of like breaking ideas down, making the implementation easy while just thinking about it, right, theoretically. Yeah, cool. So hope you guys enjoyed the video. Yeah, let me know if you guys like this type of content. I'm kind of new to this, so um, yeah, I just find it fun to like kind of like talk about these problems. But yeah, have a good one, guys.